Let us go ahead and solve two examples to, on the one hand, relate stress to strain and see some of the things that we should keep in mind, and also some additional issues about the expressions for stress components, their signs, directions, etc. So the first example is a simple example to demonstrate the idea about the orders of magnitudes of quantities as well as certain relations that we should keep in mind. So we have earlier determined solved an example for the shear and tension of a plate, and there determined the normal strain and the shear strain components that were non-zero. So for that deformation, so I'm going to say recall plate example. Find stresses for steel. Okay, so we'd like to find the stresses in the case when the plate is steel. So here I think it's a good idea to keep in mind the orders of magnitude of some of the quantities like the Young's modulus and the Poisson ratio. So the order of magnitude quantity, order of magnitude of a quantity is typically indicated with the sign, if you like, a italic O, and the order of magnitude goes inside the parentheses, and I could write here a number like 50 or 20 or 100, 10, and so on. So what that means in words, in a daily life, let's say, terminology, is I give you a number, and the real number will fall in the vicinity of that number, just to give me an idea about the order of magnitude I should be expecting. So for instance, if I want to take a walk from the campus to the center of the city, the order of magnitude for that trip is going to be, say, of the order of 2 hours. So as soon as I tell you, give you the number 2 hours, you know that it's not going to take a day and it's not going to be a 10-minute walk. So you have a pretty good idea of what you should expect. Okay, so therefore it's a useful quantity to keep orders of magnitudes for quantities in mind, and eventually make use of them if necessary. So the quantities we're looking for presently, they are the Young's modulus and the Poisson ratio, and we're just going to look at very roughly metals and polymers. So for most metals, the Young's modulus falls somewhere between 10 to 100 GPa. Okay, so that's a range. It's a fairly good range, so it can be less, it could be 5, it could be 300, but it's most likely not 1000 GPa, and it's most likely not 0.1 GPa, right? So order of magnitude wise, that's a good range. Now for polymers, which are much more easily deformable for a given amount of stress, the range is less, smaller in magnitude. So here we see that the lower bound is 2 orders of magnitude smaller. That's what one says when one observes a ratio of 100 between these two numbers. So that's 2 orders of magnitude on the logarithmic scale, if you like. And then here there's a 1 order of magnitude difference between the upper bounds. So, but still overall, you see that polymers are much less stiff compared to metals. Now, in terms of the Poisson ratio, if you just don't remember a value for a back of the envelope calculation, you can take the Poisson ratio for a metal to be 0.3. In reality, it can be 0.27, it can be 0.34, right? But we're just going to take 0.3 as a reminder of what it might be or what it might be close to. Now, the difference between 0.24 and 0.3, the real value and this order of magnitude value in practice would be large. But if you just want to do a quick calculation to get an idea about what is going on, this is a good value to keep in mind. Such back of the envelope calculations, such quick analytical calculations, both in terms of numbers and in terms of quantities and in terms of formulations, is an important aspect of this course. Modern engineering relies on intricate and very detailed numerical tools that are able to make use of very well tested theories, which are often not easy to use analytically for quick calculations but could be very accurate. We have to eventually learn how to use those, but before that we have to understand the fundamentals, and that's what we are trying to do here. For polymers, for the Poisson ratio is a good value to keep in mind is 0.5. Now at this point you may want to go back and look at the expression for the bulk modulus. For the bulk modulus, when the Poisson ratio is 0.5, it becomes infinite. When it's infinite, what that means is that if you want to induce a certain amount of volume change on a polymer, you have to apply infinite amount of stress, or vice versa. If you apply a finite amount of stress, because the bulk modulus is going to be infinite for this Poisson ratio, the volume change is going to be 0. So that latter case is what we encounter in practice, and which means that for reasonable amounts of stresses, the polymers are observed to lead to almost no volume change as they deform elastically. Okay, so this actually is an expectation that one observes physically, and the Poisson ratio is an indication of that observation. In reality, it may not be 0.5, it's going to be 0.4995, let's say, for a polymer which does display this type of incompressible material behavior. We're just going to call it 0.5 presently. That's the upper limit for the Poisson ratio for an isotropic material. Okay, so having said that, we can also keep in mind that for steel, for instance, the Young's modulus is about 200 GPa, and why don't we keep in mind the value for aluminum as well, which is 70 GPa. So these two values we're going to come across quite frequently. Okay, so now this question expects us to remember orders of magnitudes of quantities for at least steel. So I will immediately take E to be 200 GPa. The Poisson ratio is going to be taken as 0.3 according to this let me say number that we are keeping in mind. So then the question is, what are the stresses? So you will remember from our plate example that there was a normal strain epsilon y, which, as we've discussed, in the present capacity of our knowledge is going to cause only a normal stress along the y direction again, and this value was 5 times 10 to the minus 5. Now additionally, we observed that there was a shear strain, which is 2 times 10 to the minus 5, and according to our knowledge, which I already verified is correct for isotropic elastic materials, this is only going to cause a shear stress through the relation where the shear modulus appears. So therefore, the result for the stress is, for normal stress, 200 GPa times 5 times 10 to the minus 5 gives us a value of 10 MPa. So this is like 210 to the 3 MPa, 10 to the 3 cancels that, 10 to the minus 2 cancels these two zeros, 2 times 5 is 10 MPa. Okay, so now then we have to write the value of the shear stress, find the value of the shear stress, where, however, we have to eventually calculate or need what the shear modulus is. And here again, we have to remember that the shear modulus is actually expressible in terms of the two fundamental parameters were provided. It's an isotropic material. Okay, goes without saying in this case, unless indicated otherwise, we assume so. And two parameters are given. I know that any other parameter is a function of those. And in this case, the function, we don't have to memorize this. but it's not hard to remember. E over 2 1 plus nu, and that gives rise to a value of about 77 GPa. So then again I can go ahead and write here 77 GPa times 2 times 10 to the minus 5. So just like here, this is 10 to the 3 MPa. Same thing goes there. You do your simplification and find that you would get a stress of 1.54 MPa. Okay. So in this simple example, together with some knowledge of orders of magnitudes of quantities, we were able to, for a given amount of deformation, we were able to calculate the strain, right? This part has to do with the plate example, and now in the context of this particular example, from the strain we can go to stress. So we take ourselves all the way from deformation to stress, and if we're given some information about the geometry, we could multiply these with relevant area components and go towards a load if necessary. Okay, so this part presently we're not doing, but we're gonna do something reverse next. What we would like to do is, suppose some load is provided, I'll try to calculate the stresses, and from these we will try to calculate the strain. So let's have a look at the reverse scenario, and because we are given some information about the geometry, we could eventually go from the strains to deformations, but we're not going to do that in the next example. We're going to do only the first two steps. All right, so, well, here's our example, and this is a nice example because it makes a connection to the content of ME 231, and that content is something we should never forget, because ultimately we are learning about material behavior. We're going to build upon our knowledge about material behavior, and we're going to take it much beyond simple linear elasticity. In fact, even in linear elasticity, we were in ME 231 in a rather limited context. We're going to go far beyond it, but ultimately we're doing all of that so that we understand material behavior better, but in the end we want to apply it to certain problems of structural interest. So here is a simple structural problem. We have a rod, and let's say it has a circular cross-section such that eventually it is bent, it moves along one direction first, bent towards another direction, and then bent again towards yet another direction. The directions are X, Y, and the vertical one is Z. Okay, so this is the Z direction. This is the Y direction. And this one here is the X direction. Okay. So the beam is fixed on one end. Okay, and we are given the lengths of individual portions. So this portion is of length L3. This portion is of length L4. The structure is loaded through a load along the -1 direction at the top portion over here. Okay, and that load is simply P. And eventually we will be interested at a cross section here, point B, and the relevant lengths here along the x-axis are L1 and L2. And the question is rather simple. Well, it has two parts. One, stress at B1. I'll tell you what point B1 is. It's a point on the cross-section of B. And two, strain at B. Okay, so if we were asked directly the strain, of course, we have to calculate the stresses anyway, but I'm structuring the problem in this case for you. All right, so, well, what we will do first is we'll take a cut. These points, the point B lies, B1 lies on the cross-section at point capital B here. So I'm going to take a cut of this portion and draw it once again over here. So we have the support. This is point B, support at A. The beam is supported fully at that point. This distance is L1. And why don't I zoom into this cross-section now and draw it more clearly over here. Okay, so here the axis of the beam, it is the direction X. That's the axial direction. And the other two directions are respectively Y and Z. Okay. And this here is the center of the solid cross-section. And the radius of the cross-section, let's say, is R. Okay, that's the outer radius of the cross-section. And point B1 is a point that is located on the outer surface along the y-axis. Okay, we could have chosen another point, just let me indicate for possible discussion, another point B2, but we are going to be interested at that point. Okay, so that's the question. What is the stress and ultimately what is the strain at point B1? Now we're going to solve this example in the limit of our focus that we already practiced in ME 231. Okay, we can actually go beyond that focus and consider more than what is presently asked geared towards ME 231, but we're not going to do that. But ultimately, or in fact very soon, you're going to see what the missing pieces of our discussion here will be. Okay, but this discussion presently is limited to ME 231. So we're focusing on that picture. So we're going to start with part 1. And to start with part 1, let me first draw the cross-section yet again. All right, with the axes Y and Z, and the alto plane direction, remember, is the alto plane direction is X. Okay, and we are looking at a point B1 that lies along the y-axis, and there is ultimately another point, if you like, B2 along the z-axis. Now, first of all, what I need to do is I need to represent the statically equivalent counterpart of this loading on that cross-section and transfer it over onto this picture so that eventually I can find the stresses. Well, why don't you take at this point to think about the types of loading that I should express on that cross-section due to this tip load P on the beam. Okay, so in general you can have forces, moments, etc. So that's what I'd like you to find here. So here you can pause and think as long as you like. I'm just going to continue. So first of all, when I move this load to that cross section, it's going to cause a torque. It's going to cause a bending moment, and it's going to cause a transverse shear force. The easiest thing to do is to think about first the transverse shear force that one causes. So if I carry it onto that cross section, there is going to be a transverse shear force P. Okay, so typically we denote that transverse shear force with V. In this case, V is equal to P, and the direction is along the minus Y direction. That's quantity number one. Well, quantity number two, there will be a rotation. This force tries to rotate the beam about the x-axis, if you like, about that direction. Okay, but it's torquing, okay, with respect to this picture about the x-axis, so I'm going to move it over here as such. Okay, there will be a torque, and that torque will be equal to P times L4. Okay, that's the second piece that we need to incorporate into our picture. And then there is also additionally going to be a bending moment. That bending moment is going to be about the z-axis, okay, because if I look from above, what I see is a beam that is supported, okay, so I'm looking in the minus z direction, so I'm putting a cross. So here there is a beam, it is bent up like this, okay, it goes in that direction. If I look at that picture from above, so here this would be the, if you like, the x-axis, this would be the y direction, and there is a force that is applied in the minus y direction, which is going to bend the beam like this, right? So that's a bending moment in the minus z direction. So the bending moment in the minus z direction can be conveniently denoted, let's say, like this. That would be M. Or on that picture, I can draw two arrows to indicate that this is a moment, and M is going to be the force times the distance, the relevant distance, in which case, in this case, it's L2. Okay. All right, good. So that's the statically equivalent counterpart of this loading at cross-section B. And at cross-section B, we are interested in point B1. Okay. So in general, we're asked for stresses, we will have shear stresses and normal stresses. So first, let's go ahead and write all possible values that we could encounter. So the first thing we could have is obviously a shear stress. The shear stress, I'm going to start with P. There could be a shear stress due to the transverse shear force on this cross-section in general. And that would be a transverse shear stress that is, remember, in the form VQ over IT. We do not need to remember the form of Q. We should understand always how to choose T and what the value of V is and the meaning of V and value, but Q, it's for these types of cross sections not easy to remember, but still we have to interpret the equations correctly. So V is in that direction, and we remember that the transverse shear force is 0 on one surface and goes to 0 onto the other surface along the direction of the transverse shear force and reaches a maximum value somewhere in the across the way, in fact right along the z-axis in this case, because it's a circular cross-section. So 0 and then to maximum back to 0. In other words, the transverse shear stress along Z is a max. In other words, at B2 there is a value that I can calculate. At that point, T has a value of exactly equal to twice the radius, because that would be the line for that relevant line for that transverse shear stress. And I always can remember that I is equal to PR to the fourth over 4. Q I can look up, or if I have time I could calculate, but ultimately I could calculate for B2, but for B1 presently it's equal to 0, so I do not need to worry about it. The next thing I can look at is the shear force that is associated with the torque. Now the shear force is equal to Tc over J, or in this case C is the radius, Tr over J. And J is PR to the 4th over 2. Okay. If you have trouble recalling which one is over 4 and which one is over 2, you can remember that you obtain J by summing up I about Z and Y. IZ plus IY would give you the J, the polar moment of inertia, in this case Jx, really, about the x-axis, because that's the torque that's associated with that axis. And so Jx is Iz plus Iy, so twice that has to give me that value, so that's why this is factor of 2, this is factor of 4, this should be smaller. All right, so with that way of keeping, or let's say recalling things, I can easily find that the shear force is going to be 2PL4 over pi r cube. Okay. Now what I can also indicate is the direction for this force, for this shear stress. Now the direction is at that point tangential to the surface, and it is going to point downwards. Okay. So this is just the magnitude that is indicating direction. And remember, we are on the plane with normal x, so we just keep that in mind. All right, so if we were at point B2, what would be the direction of tau, t? So think about, when I ask you a question, think about it for a second before hearing the answer. Well, at that point, again, it's tangential, it would be to the right. At that point, what would be tau v? It would be to the left, because that would be the direction of the transverse shear force, etc. Okay, good. So now we're done with the shear stresses. There is no other loading on that cross-section that could possibly cause a shear stress. So next we can look at the value of the normal stress. So the normal stress is associated with the bending moment. So I'm just going to put here an M. Okay. So I'm putting here these subscripts so that we recall that this is just the magnitude of the normal stress, and it's not an X or a Y or a Z, because eventually the stress component, the correct one, sigma X, Y, or Z, has to involve not only the magnitude but also the correct sign. So in this case, this is just the magnitude, and due to bending, it's going to be MC over I or MR over I. There is the value of I, so it is PL2, that's the value of the bending moment, times R divided by pi r to the 4th over 4, so it's 4PL2 over pi r cube. And here, what's the direction? Well, it's a normal stress. It's a normal stress that is associated with the plane X, so it's along the direction of X, but plus or minus, well, I can indicate that by saying whether it's tension or compression. So in this case, the bending moment is going to compress the plane by pushing on the left and pulling on the right, because that's the direction of loading. It's always the right-hand rule. You push on the left, you pull on the right. Okay? So my thumb is pointing against the direction of the bending moment, so here it is compressive. Okay, that's going to give me an indication about the sign of the normal stress. So now I can go ahead and think about the components of the stress matrix. So first of all, let's think about the normal stress. Well, the normal stress is a stress that is associated with the plane X. So I'm going to be concerned with a normal stress on the plane with normal X. And then I know that it is compressive, so it has to have a negative value. And the magnitude is simply sigma m. Okay, so sigma m simply indicates whatever value this is, depending on the values of P, L2, and R. So that's the correct way of denoting sigma x. So then comes, well, the question, what else is there? Well, there could be, in general, a shear stress as well. Indeed, there are some shear stress as well. What kind of stresses? What are the components that they belong to? So first of all, I am on the plane with normal x. So safely, the very first thing I can do is I'm considering the plane with normal x, so the shear stresses have to have an index that is associated with that. Well, I have only one shear stress, and that's that one. And that one is on the plane with normal x along the minus z direction. So this is going to be, first of all, a tau xz, because that's the direction it's associated with. And then it has to have a minus sign, and therefore it's minus tau t. Tau t just denotes the magnitude, and it's that value. So these are the only stresses that I have, right? So depending on which point you're at, the indices might change. So for instance, the shear stress at point P is, again, it's on the plane with normal x, but it's in that direction. So now it's not going to be a tau xc, but rather it's going to be a tau x y, and it's going to be plus tau t at point B2, etc. So that's something that I'd like you to think about. How do you express, for instance, stresses at point B2? So with these, we can go ahead and also write the expression for the stress matrix, and we can say that, well, sigma x is here, so it's going to be minus sigma m. There is no normal stress for sigma y or z. There is a tau xc, so this is tau xy, this would be tau xc, so minus tau t, and then it is symmetric. So these values are 0. I'm sorry, this is supposed to be minus tau t. This is tau xc, this is tau zx. They're equal due to the symmetry of the matrix. All right, so that's the way we would depict the stress. So next, well, what are the strains? Let's answer that question. Now, the strains come easily. Well, first of all, I know that sigma is equal to E epsilon, so if I divide both sides through E, I can find that epsilon has to be sigma over E. So in this case, I have only a sigma x, and therefore I will have an epsilon x. And therefore, epsilon x is simply going to be minus sigma m, which is that value, for PL2 over pi r cubed divided by E, which is equal to E. Okay? And then we will have a similar relation between shear strain and stress. I know that tau is equal to gamma g. In this case, I have only tau xc, so I will have only gamma xc or gamma zx, and they are equal, right, due to symmetry of the strain as well. And it's going to be tau xz over g, which therefore is equal to minus tau t 2pl4 over pi r cubed divided by g. Okay. Now, we are in a good position now to make a connection of what's going to come next and make a connection to what I said earlier to reinforce that. Now, I said that we are looking for at isotropic linear elasticity, and the relation between shear stress and strain, it's nice, and well, what does nice mean? It means that it works well without any problems, but it turns out that there is a problem with this relationship. Now, in this relationship, it turns out this, what I have written, is correct, no problem with it, because there is no sigma y or sigma z, and it's very important they are not there, because if they were there, it turns out this relation is not correct. But there is something missing. I'm only looking at epsilon x. Well, is it possible that there's an epsilon y, and is there an epsilon z, etc.? So I need to also think about that, and I seem to omit that picture presently. But omitting all of those in the context of ME 231 was safe, but now we need to go a little bit beyond, and that's what we are going to do next.